finally at the ideal market prediction competition results. We're going to do a quick analysis on looking at the competition from above, let's say, and looking at the behavior of submissions. As it was mentioned before, we have a number of submissions, and I would like to stress that many people did a great job, beside the top 10, of course, and that this should be appreciated. So let's jump into this analysis, and then we can announce the winners. So the problem statement, it was a problem about financial markets and a machine learning, as we said, domain agnostic machine learning exercise in which the goal was to rank future outcomes of financial instruments relatively. So as many of you may know, it's really difficult to predict the future behavior of one asset, the future price. It's much easier, even though more constrained, to ask ourselves the relative performance of a set of assets. So for this, the goal was to rank assets relatively, and so the fitness function was a Spearman rank correlation that relates the order of a set of assets defined in a cross-section. Of course, many investment strategies can be built on these ranks, and we would like to follow this analysis of the set of predictions on a way in which these predictions can be put together to power an investment rationale.
So this was about the problem statement, so trying to predict the relative performance of assets. And to do that, we divided the competition in two parts. Some of the subject that has been described by Professor Marco Lopez de Prado and Dr. Simon during the panel have been inspiring many of the design choice that we made. The first one was dividing this competition in two parts. The first part, during the week 0 to 12, the participants and the machine learning engineers, the data scientists, the researcher of the CrunchDAO community could access a part of the data that they had to work with, and they could build a model on this data. They could submit the code that could create the inference, so create the prediction of the model that they built. During this phase, they had a direct feedback loop. They had a direct scoring. And so they could see as well the relative performance between their models and the models of other players. And this is called in the machine learning competition framework a public leaderboard. So for the week 0 to 12, all the players could see their relative performance. And that has some interesting implication that we will describe later. This data set was, of course, anonymized, so they didn't know what kind of data they were actually looking at. They didn't know what was the asset they were working on. They didn't know what kind of target they were training with. They just had to look at this problem from a quantitative perspective and try to maximize the scoring metric that is Spearman rank correlation. At the week number 12, we blocked further submissions. So the player could not engage with their submission. They already submitted their code, and they were not able to modify this code. And during the week 12 to the week 24, we ran their models, we retrained their model, we produce some inferences, and we score these inferences. And this is an out-of-sample period, also known as private leaderboard. So this is very important, and we will describe it later, because it allows us to be sure that there is no interference from the player, and what we are scoring is actually the same object for 12 consecutive weeks, facing data that was never shared with the scientist. And one of the main particularities that was at the heart of this design is what we call a code competition. So instead of submitting just their prediction, which is quite common in machine learning competition, and which is also quite convenient, they had to submit the code to produce new inferences. And this is very important because thanks to this submission of code, we could actually have a better interpretation of the result. We could look at the feature importance of the models, for example, and we could basically avoid working on the black box. So Professor Marco Lopez de Prado was mentioning this black box, and also Dr. Simon, this black box effect. What is interesting when someone submits the code, the main interest is that you have more interpretability of this submission. The second interest of the code competition is the robustness. When we execute the code of the user, well, we are in charge of producing the inferences. So there is no intervention of the players. This is more robust because we don't depend on the player to resubmit the prediction every week, right? To test this code on data that he never seen. Then with this system, we have more agility. Why? Because first we can retrain the player, but we can also, for example, send a different type of data to this model. So we could send noise, for example, noisy data, change the level of noise, and see how the model reacts to this perturbation. Well, in terms of IP for the players, we are in the exact same use case. All the users that submitted code during this competition maintain their IP, and this is very important. They are still owning the model. And in terms of integrity, we make sure with a code competition that everyone use the same amount of resources, the same amount of computing powers, and that all the submissions are compliant to the rules of the games, and that all the submissions are actually fair. Then, to support this specific vision that has at heart replicability, reproducibility, etc., we had to develop a complete custom infrastructure that we didn't have at CrunchDAO before. That was very interesting, and we coded this infrastructure that actually can receive code. And that's not trivial things, because you have to think that we had to execute code of users that we don't know, that we never met, on our infrastructures. And that's very delicate, especially when you connect computing power to these resources, because it can be used or abused. So we developed this system in partnership with AWS and NVIDIA, which provided us with the computing resources that was necessary to retrain and run all these models and codes. And all the system went through a complete audit from AWS to make sure that there were no possibility to cheat or to exploit outside information or even abuse the computing resources. Now I'm giving you the mic, Matteo, for this
Thank you.
Analysis.
Yeah, thank you, Jean. So let's take a look at the analysis of the competition, and then we will announce the results. I'd like to start from a benchmark model that we had internally, that we developed in the analysis of the dataset. And this is the performance. I'm going to show a number of figures now in which the y-axis is basically what you would have seen on the live leaderboard. So it's the rolling average on an expanding window, starting from the beginning of the auto sample of the Spearman correlation cross-sectionally. So this is our benchmark model. And you see that while there is a bit of volatility at the beginning, of course, because not many cross-sections are realized, this model converges to around 5% Spearman rank correlation. And this is basically the set of all the selected summations for the auto sample. And you see that this kind of dynamics at the beginning resembles the benchmark model. However, there's a really high density, and then I will show you how non-Gaussian the distribution of scores is, particularly at the end. But you see that there is a high density of performances higher than the benchmark model, and you can see it on the right. Here are the top 10, so the actual winners of the competition. You see them colored among the set of all the submissions. Another thing I didn't stress is that, as I said before, congratulations to really a number of people participating, and also because of the fact that just, I think, 2 people, maybe even 1, had the negative score at the end, so really impressive. But yeah, you see that it was like, I don't know, we were talking about the race of Usain Bolt versus I don't know who else, but it was really a tough competition. So here is the distribution of the final scores. As I said, it's really impressive how people, you can almost see the boundary of all the possible information you could have squeezed out of this data set. And many people push to the limit. Then there is quite a long tail on the left, and actually this resembles a bit the distribution we see in quantitative finance, so skewed high kurtosis. Here is what Jean anticipated. So we are comparing the performance of the public test set with the out of sample. As Jean anticipated, in the public test set, there is this implicit possibility of overfitting as the user is adapting his or her behavior, to the feedback of the public leaderboard. Also, there is the incentive of looking good on the public leaderboard. So there is this wheel of consciously overfitting the public leaderboard. So you see on the x-axis the public test set score, which is the public leaderboard score at the end of the first phase, and the y-axis the out-of-sample score. All in all, there is a good correlation. But basically, you can detect kind of two interesting behaviors at least. The first one is the overfitter, in which you can see that the public test set score is high compared to the relative out-of-sample score. So here there is a willful or unwillful overfitting. But the majority of people actually, probably consciously, and we had interactions in our channels on people explaining how they decided which model to select, and many of them used in a non-trivial way the feedback of the public leaderboard to select the final model. It was not just the highest score on the public leaderboard. About the auditability, the code competition allowed us to analyze the effect of, for example, stochasticity of the models. So when we want to understand why a data generating process leads to a high information coefficient, one of the reasons could be easily, in the context of machine learning, the random seed associated with some stochastic technique. In fact, here we run the overall out of sample twice, and we looked at the difference in scores for the same model, for the same data set. So the code is the same. There is just one random seed that's not specified in the code. So bad practice.
If I may add, I think this is also one of the points that was discussed by Dr. Simon when you talk about the stochasticity that is involved in very complex model. Maybe those players were using very complex method that actually don't give the same result at all in some period. It's actually quite dramatic, and it was very interesting to witness as well.
Yeah, of course, and this is actually, it's kind of what you said about being able to inject on-purpose noise on the data to see the robustness of the model. Here, it's happening the opposite. So the data is the same, but there is this stochasticity appearing, and if the user is not careful, there is a 3 sigma difference of a few percent points in Spearman correlation, which is non-negligible. This is actually the difference in score at the end, looking at, for example, we have the same model going from a 4-point-something% to a 3.5-ish. So it's not trivial variation of score. So the actual estimation of the auto-sample performance cannot be done, it has to be done taking this into account. A final slide, I believe, before announcing the winners. And we did an analysis on trying to put together the set of predictions. This analysis is done just performing a rank-based ensemble average, looking at the k-best submissions. Of course, defined in a look-back window. You can think that on top of the competition, we performed another competition on the out-of-sample, in which we define a first period in which to train our model, which is a one parameter model. And we looked then in the remaining part of the out-of-sample, looked at the performance. The interesting result is that regardless of the in-sample size that's introducing, actually it's two parametric model. We're defining the in-sample size, and we are defining the number of k best defined on the partially resolved autosample. And in this space, you can see that for independently of the in-sample size that introduces a bias, there is an increase in out of sample squared, let's say out of sample in this out of sample performance as a function of increasing the number of k best, which is showing the value of the wisdom of the crowds, as in particular the first column would be a strategy that constantly follows the winner only and counts on just one model. The more the regularizing behavior of ensemble averaging leads to an increase in out-of-sample performance, regardless of the in-sample size, which is a remarkable result. And I guess it's time for the ceremony.